Hello everyone. This is part 2 of topics 3 through 5 for exam 2, and last time we saw situations that required the use of the integration formulas that result in the inverse trig functions, and we also saw in comparison situations where it fit what I'm calling the basic forms. So number 1 and 3 were situations where they resulted in the inverse trig functions, and 2 and 4 were the basic forms. Now, when I say basic forms, I either mean u to the n or du over u. And with regards to our integration strategy, when we see a fraction, we still consider asking the question, is the denominator a power? And if it is a power, we go for u to the n. If it's not a power, we go for du over u. But then we extend our strategy, and if it does not fit one of these two basic forms, then we consider the integrals that result in the inverse trig functions. Now, if we look at question number 5, here we have a situation where if the first question we ask is, okay, it's a fraction, is the denominator a power? Yes, it's a power because it's under the radical, so therefore we try to fit the form of u to the n. And you don't have to write this down. I'm just going to justify why it's not going to work. If it were to fit the form of u to the n, we would rewrite it by writing 1 over x and then swinging the quantity 25x squared minus 49 up to the numerator. It would be raised to the negative 1/2 power, 1/2 because of the square root, negative because of the shift from the denominator to the numerator. And in an attempt to fit the form of u to the n, which again, you don't have to write this down because it's not going to work, I'm just justifying why it's not going to work, our u would be chosen to be the quantity, 25x squared minus 49, our du would be 50x dx. Certainly we could modify by the 50, the problem is we don't have an x, we have a 1 over x. So that's why this method would fail. So then we turn our attention to the integrals that result in the inverse trig functions. And to get a start on the problem, all you have to do is classify. You look at the fraction, there's either a radical in the denominator or there is not, because consider the 3 formulas that we have. Square root of a squared minus u squared in the denominator, a squared plus u squared, no square root, and then another one with the square root of u squared minus a squared in the denominator. So what you do is you classify. If there's a radical, classify what's underneath in terms of a squared and u squared. And just remember that a squared is the constant and u squared is the variable. So the 25x squared represents the variable u squared. The minus is part of the formula, and the a squared is the constant 49. Now, off to the side, we're going to start the u substitution process, but recall that it requires us to choose a as well, and as a crutch, we claim that a squared is 49 and u squared is 25x squared. Again, neither are ever negative, and that was just a crutch, as I said, because the concession we make if we take that step is to take the principal or positive square root, and a is 7 and u is 5x. And before we go any further, if you want justification that we're headed in the right direction, just look at the formulas and you see we do have a form for the square root of u squared minus a squared here. But there's a u out in front that we'll deal with momentarily. But continuing, this is still just basic u substitution, and so the du has to be calculated, and that's 5 dx in this case. And so we modify routinely to get that 1/5 du is 5 dx. Now, when we go back to the formula, 1/5 du is just simply dx. When we go back to the formula and we consider the leftovers, well, besides the 1 dx that will satisfy the du, just modified by 1/5, we also have this x. So there's a couple different ways to go about this, but here's the first way I'm going to show you. I'll replace the 1/5 I'll replace dx with 1/5 du, as we normally would. But then I have to account for this, for the fact that in the formula, there is the square root. Out in front of the square root is a u. And u in this case is equal to 5x. And so therefore what I'm going to do is I'm going to slide a 5 in front of the x to satisfy my u that's out in front of the radical in the formula. But I can't just do that. I have to compensate, and therefore I multiply the numerator by 5 as well. But now this 5x that I forced to be in the denominator, now that represents the u. And so with the change of variables, this is equal to, okay, I've got the black 5 that was used to compensate for the 5 that I forced in the denominator to help make up the u. And then we've got the 1/5 from our du right here. And then the integral of, upon the change of variables, now we have du over u and the square root of u squared minus a squared. And now it fits the form right here that results in 1 over a inverse secant of u over a. The 5 cancels with the 1/5, so we just get 1 over a inverse secant of u over a, actually absolute value of u over a, and plus or constant, and then we can back substitute, and a was 7, so we have 1/7 inverse secant, absolute value, u was 5x over a, which is 7, plus the constant. So that's one method, and I just want to show you another method, although there's even a third method, but I'm not going to show you that one. When you get to this point where you have, I'm just going to show you the setup of it. Again, this is an alternative way to proceed. You would take the same out where you classify u squared minus a squared under the radical, and you calculate you find your a, you find your u, and you calculate your du. But when you substitute the 1 over x, which is 1/5 du, you could actually let the 5 in the 1/5 be the coefficient of this x that's in the denominator. So there's 1/5 du, and then this automatically satisfies the u that's out in front. And upon the change of variables, you identically have du over u and the square root of u squared minus a squared. And then you could finish that off the same way that we finished it off here. So that's a more glib approach, glib meaning smooth. This is what I call brute force. Your choice, you could proceed either way. I actually like the brute force method because that's a technique of integration that is sometimes employed, but it's your choice as to how you want to proceed. Okay, so now we have a series of, so those were all basic examples. And by basic, I mean our u ended up to be just a function of x that was linear. Actually, this next example, example 6, is a definite integral. And I made the integration real easy on this one, because same reasoning as before. If we tried to fit u to the n, it would fail, because we don't have an x in the numerator, we have an x in the denominator. So we'd proceed by classifying u squared minus a squared again. But here it's kind of silly to choose u and a, because a squared is 1 and u squared is x squared. And if a squared is 1 and u squared is x squared, then a is 1, u is x, du would just simply be 1 dx or dx, and there's no modification by a constant multiple necessary. That is, we already have the square root of u squared minus a squared, there's a u out in front, and the 1 over x satisfies the du. So it's kind of silly to make a u substitution, because, I mean, if you want to, you could. You get 1 over a inverse secant absolute value of u over a, but kind of silly to do so because a is 1 and u is x, so you just get the inverse secant of the absolute value of x. Now this is not plus c, this is a definite integral, and so therefore we use the vertical bars to being evaluated, and it's going from -2 to the square root of 2. And let me actually make a correction there. This really shouldn't be -2 to the square root of 2 if you make a u substitution. And it should be a to b. But actually it is correct to say that because u is equal to x. So I guess we can leave that, because it's not wrong in this case. And so then, by the fundamental theorem of calculus, we put in the upper limit. Inverse secant of absolute value of the square root of 2 is just the square root of 2, and then minus inverse secant absolute value of -2 would be 2. Okay, and now here's the part where we're going to fill these in. To do so, we go off to the side, and we got to do some work that most students don't like. We're going to let y equal the inverse secant of the square root of 2, because we're looking for the angle y, and it's equal to the inverse secant of the square root of 2. So by definition, the secant of y is the square root of 2. Now, I'm going to make that a ratio by putting it over 1. First off, what quadrants could we be in? And that's based on secant being positive. If secant is positive, that's the same where cosine is positive. Quadrant 1 or quadrant 4. But we're going to be able to eliminate one of those quadrants based on the range of the secant. And if you look at that one formula sheet we had a while back, when we first defined the inverse trig functions, the range of the inverse secant is 0 to pi over 2, inclusive at 0, non-inclusive at pi over 2, in union with pi over 2 to pi, non-inclusive at pi over 2 to pi, and inclusive at pi. So based on that range, we know that 0 to pi over 2 represents quadrant 1, and pi over 2 to pi represents quadrant 2. So therefore we can eliminate the angle in quadrant 4, because based on the sine SIGN of the secant of the angle being positive, we could be in 1 or 4, but the range restricts us to 1 or 2. So we eliminate 4, and we start our routine. Pick a point, drop a perpendicular. Here's our angle y. Secant is defined as hypotenuse over adjacent. hypotenuse square root of 2, adjacent 1. Immediately, you know, that's your 45, 45, 90. The same opposite side is 1, and y is 45 degrees, which you could change to radians. Pi over 180 gives us pi over 4. And so here we have pi over 4, and then minus the inverse secant of 2. And for the inverse secant of 2, we do the same thing. Let y equal the inverse secant of 2. Then by definition, secant of y is 2. We'll express that as 2 over 1. Good thing is we don't have to argue the same thing over again about the quadrants. We know we're in 1 again because it's positive. So just working in quadrant 1, the right triangle, reference angle, or the actual angle theta. Again, hypotenuse over adjacent, hypotenuse 2, adjacent 1, opposite radical 3. And because 2 and 1 immediately triggers the radical 3. Y being opposite radical 3 is 60 degrees. Unit conversion, pi over 180 gives us pi over 3. So we have pi over 4 minus pi over 3, common denominator of 12, 3 pi over 12 minus 4 pi over 12 gives us negative pi over 12. Okay, so that one, all this stuff here was kind of a little bit of work, but at least we made the integrations easy. Okay, continuing. The rest of these problems involve special situations. In question number 7, we have a fraction. Denominator is not a power, so we would try du over u, but that fails because if we're trying to fit the integral of du over u, you can tell that by inspection. You don't need to write anything down, because if you took u to be this denominator, the derivative is 8t to the 7th, and that obviously we don't have the t to the 7th here in the numerator to satisfy our du. And I think I'm going to stop here for this one because there's a lot of delay in this video. So I'm hoping the next one will be better. So I'm going to stop and we'll pick up a part 2 at this stage.